Welcome back. In this lecture, I will discuss frictional properties of polymer molecules in dilute solution and give you an overview of polymer molecular weight determination techniques. We have started discussing characterization techniques of polymers, and in the last lecture we have discussed chain dimension. Now, frictional properties of polymers also related to chain dimensions, as we can basically anticipate that if the polymer chains becomes larger in size, then the viscosity of the polymer solution will be higher, which means the dimension of polymer chains had very close relationship with the frictional properties of the polymer solution. And let us discuss frictional properties of polymer in this lecture. We will consider dilute solution because for a concentrated solution we are not interested at this moment, because most of our polymer characterization techniques are done in dilute solution, and we are learning these frictional properties which will help us to understand the techniques which are used to determine polymer molecular weight. Now, there are two types of polymer molecules can be possible in solution. One is free draining polymer molecule. In this case, solvent molecules flow past each segment of the chain. So, basically solvents do not intermingle with the polymer coil. In fact, we do not have polymer coil in this particular case. If I have a rod like polymer structure or very short polymer structure, then it basically flows through the solvent without interacting too much with the solvent molecule. So, basically solvent molecules flow past each segment of the chain, and this behavior dominates for the very short chain and highly elongated rod like molecules. Now, these polymer molecules are not very frequently encountered. Most of our regular synthetic polymers are not free draining type of molecules. So, we will not discuss this topic to a higher extent. Most of our synthetic polymers, they behave non-draining polymer molecules in solution, which means solvent molecules within the coiled polymer structure move along with the polymer molecule, and this behavior dominates for flexible long chain polymer molecules, which are the generally encountered polymers in our most of the applications. Now, in this case, non-draining polymer molecules, the molecule or the polymer molecule can be represented by one equivalent impermeable hydrodynamic particle, that is one which has same frictional coefficient as the polymer molecule. Let me explain this little more. Say if this white one is the polymer coil. Now, just like any other molecule, this will have Brownian motion, and it will have so basically it will undergo translational motion through the solvent molecule. Now, when it moves, it will move along with this small solvent molecules which are shown here. So, when this polymer coil actually travels across the solvent, it moves along with these solvent molecules which are present in the coil. Now, we can represent this as a impermeable hydrodynamic particle like this, spherical particle which has the same frictional coefficient as this polymer molecule. So, in this case we are considering an equivalent rigid or impermeable hydrodynamic particle which has same frictional coefficient as a real coiled polymer chain which moves along with the solvent molecules. Now, for this hydrodynamic particle we have corresponding volume which we call hydrodynamic volume, which is represented at Vh, and we have corresponding hydrodynamic radius and hydrodynamic diameter. So, when you talk about hydrodynamic size, then we can talk about either hydrodynamic radius, diameter or volume. And dynamic light scattering technique is actually used to determine the size, hydrodynamic size of a polymer particle or polymer molecule in solution. Now, we will talk about Einstein equation for viscosity of a suspended rigid non-interacting sphere as we described in the last slide. We talked about a impermeable hydrodynamic particle effectively which does not interact with the solvent molecule. The frictional coefficient of which is same as the real polymer chain along with the solvent molecule. So, the Einstein equation is given by this, where this is the coefficient of viscosity of the solution and this is the coefficient of viscosity of the solvent, and phi 2 is the volume fraction of the solute which is polymer in this case. So, this is the suspending medium which is the solvent in this case. Now, specific viscosity, we know specific viscosity eta Sp is given by eta 0 minus 1. So, from there if we know this expression of eta specific viscosity as this, then we can rearrange this expression as this, where C is the polymer concentration in terms of mass per unit volume, m is the molar mass, Na is the Avogadro number, and Vh is, as described in the last slide, hydrodynamic volume, which is the volume of rigid non-interacting sphere. Now, we know intrinsic viscosity, which is given by limit C tends to 0 eta Sp by C. So, if we rearrange this expression, we bring C in this denominator, then we can write intrinsic viscosity as this expression, where we are writing Vh hydrodynamic volume when concentration is tending to 0. So, we can write, because we are talking about very dilute solution, then we will not write this subscript C tend to 0 now onwards, we will write simply hydrodynamic volume. So, the intrinsic viscosity is proportional to the ratio of hydrodynamic volume divided by the molar mass. So, intrinsic viscosity is inversely related to the density of the random coil, because this is 1 over density, effectively 1 over density of the random coil. As the density increases, the intrinsic viscosity goes down and vice versa. So, denser the coil volume, smaller is the intrinsic viscosity, and for a chain which has same molecular but lower hydrodynamic volume. In case we have a branched chain, then for a given molecular weight we can have a lower volume, hydrodynamic volume, then the intrinsic viscosity will be smaller. Now, if we multiply it, we can rearrange this expression, take this m to left hand side and we can get this expression, whereas now this shows that the multiplication of intrinsic viscosity and molecular weight or molar mass is proportional to the hydrodynamic volume. So, this term intrinsic viscosity multiplied by the molar mass depends only on the hydrodynamic volume. So, if there are two chains with same hydrodynamic volume, irrespective of their chemical or structural differences, if they could be branched, they could be linear, or they could be of different chemical nature, but if their hydrodynamic volumes are same, then their product of molar mass and intrinsic viscosity also would be same, and this is the basis for universal calibration of GPC, which we will talk in a later lecture. So, we can, as if we have seen this expression before, so we can say that intrinsic viscosity is proportional to VH by m. Now, hydrodynamic volume can be expressed as the radius of gyration. It is like the radius of that hydrodynamic particle. So, the volume would be 4/3 pi r cube. So, this is kind of r. So, this is hydrodynamic volume is proportional to the radius of gyration to the power 3. Now, we know this radius of gyration can be expressed as the unperturbed size and the expansion factor. So, we can write in place of VH, we can write this term. So, instead of proportionality, if we write equal, then equal sign, then we have a constant. This is the constant and we have this same expression. Now, we can rearrange this little bit, take this within the bracket 3/2 and put 1/2 outside, and we can further rearrange as this. So, radius of gyration divided by molecular weight to the power half, and which is raised to 3. Now, we have seen in last class that this term is related proportional to the root mean square end to end distance, which is proportional to n to the power half. N is the number of bonds, so which is proportional to the molecular weight to the power half, which means if we divide this with m to the power half, then this would be a constant term. So, this means the term inside this bracket is constant. So, we can put this constant and this constant together, make a new constant k, and write the entire thing as k, and write these two other quantity to write a expression like this. So, this is the constant which accommodating the entire these terms, and I explained why this is a constant. This expression is called Flory-Fox equation. This is the expansion factor for radius of gyration. Now, for theta solvent, which is the basically below which we get poor solvent, and the chain dimension is minimum in theta solvent. So, for theta solvent we know, for theta solvent we have this value of S as 1, as we have seen before. Now, for dilute solution, when the solvent quality is good, this is actually proportional to m to the power 1 over 10, which means this term is proportional to m to the power 3 by 10, which means when we talk about these two terms would be proportional to m over 0.8. Now, this happens for solvent which is good solvent for this polymer. So, this is in this case for a poor solvent or theta solvent we have m to the power 0.5, and in this case we have m to the power 0.8. So, if you write instead of these two constant together, if you now take this together and write eta is equal to some other constant m to the power a, then a would be varying from 0.5 for a theta solvent to 0.8 for a expanded coil in a good solvent. Now, it can go beyond 0.8 when the polymers become elongated and rod like shape, but which is not very frequently observed in our case. So, the value of A would be between 0.8, 0.5 and 0.8. This is for the theta solvent, and this is for the good solvent when the polymer coil is expanded, and this expression we call Mark-Wenck equation. So, we can write, as I explained, this expression. This K is another constant, m is the molecular weight raised to the power A, and K and A are constant for a particular polymer solvent temperature system, which means if any of these three quantity changes, either temperature changes or solvent changes or polymer changes, the value of A and K would also change, and we call this as Mark-Wenck equation. And later we will see that this molecular weight is actually mv, which is viscosity average molecular weight, and this will be utilized to determine, this expression will be utilized to determine the molecular weight, viscosity average molecular weight, in the coming class or coming lecture. Now, in Mark-Wenck equation, which actually was derived later experimentally, it was derived theoretically as we explained from Fleury-Fuchs equation as a empirical equation, and K are constant for a given polymer solvent temperature system as I described just now, and the value is normally between 0.5 to 0.8 for a linear chain. For elongated chain, this can go beyond 0.8, but which is not a very frequently observed polymer chain. For theta condition and linear chain, A is 0.5 as I described a few minutes back, and K increases with increase in the value of A for flexible chain, and typically this is the value for K. For branched molecule or branched polymer molecule, the hydrodynamic volume occupies smaller volume for same molecular weight. Hence, the intrinsic viscosity becomes smaller, which means A becomes smaller. So, A is kind of represent the expansion of the polymer coil. If you have a theta solvent, then it is not expanded, so value is 0.5. If you have a good solvent, then it expands, so it increases to 0.8 and so on. For a same molecular weight, if we have a branch structure, obviously the size will be, hydrodynamic size will be lower, which means A value should be lower, and the value of K and A for copolymers are very difficult to obtain, they are complicated. So, if we discussed before, so if we compare two chains, one is linear without any branch, another is linear but we have branch, which is shown in this color. Both are having same molecular weight, then we can compare between these two, that they have same molecular weight, but hydrodynamic volume for this will be higher, this will be lower because of presence of branch, and the segmental density of the coil, this will be higher, it will be more dense coil, and so intrinsic viscosity of this branch polymer will be lower compared to the linear without branch. And this is the factor which generally used to express the branching or extent of branching, which is a ratio of the intrinsic viscosity of the branched structure and linear structure having same molecular weight, and higher is the branching, it becomes lower and lower compared to 1. If there is no branch, then it will be equals to 1. So, this G prime is the value which generally used to describe or quantify the extent of branching in a polymer chain. So, just to repeat what we understood, that with increasing chain length for a linear molecule, density decreases, intrinsic viscosity goes up. If we increase the mass of a chain, so density increases, keeping the length same, the density increases, intrinsic viscosity decreases. If we increase the stiffness of the chain becomes more elongated, hence the intrinsic viscosity increases, density goes down, and as we discussed earlier, if we add branches keeping molecular weight same, the density increases and intrinsic viscosity decreases. Now, we talked about this hydrodynamic particle of a polymer chain. Now, the translational diffusion coefficient of this isolated polymer chain is related to frictional coefficient by Einstein equation like this, where this is the diffusion coefficient, translational diffusion coefficient, K is the Boltzmann constant, T is the temperature, and F naught is the frictional coefficient. Now, these are linked, this frictional coefficient is linked to the hydrodynamic radius by Stokes equation. So, we can relate, if we found out the diffusion coefficient, we can use this expression to find out the size of the hydrodynamic particle, which is done by using dynamic light scattering, which I will discuss in a coming lecture. Now, let us move to the molecular weight determination techniques for polymer, and as I mentioned earlier, there's most of or almost all molecular weight determinations are done using dilute polymer solution, and that is why we were discussing or understanding the polymer behavior in dilute solution. So, while we use different techniques, we must remember or understand the different aspect of various techniques. For example, whether the technique is relative or absolute. Relative in the sense that the reported molecular weight values are in relative to some other known values, or it is absolute value. For relative measurement, we require a calibration curve from polymer chains with known molecular weight, but for absolute technique we do not require any calibration curve from known molecular weight. You also need to know that what are the type or types of molecular weight data the technique can provide, whether any additional data it can provide, and what are the limitation, which includes what is the range of molecular weight of polymer which can be determined by that particular technique, and what are the special cares should be taken to accurately measure the molecular weight. So, I will give you the overview of the various techniques. These first 4 techniques are based on measuring the colligative properties of polymer solution, which depends on the number of solute molecules, in this case polymer molecules in solution. So, these techniques gives number average molecular weight. Membrane osmometry is a absolute technique, whereas the other 3 are relative techniques. Now, this star means that although in principle it should be able to provide absolute value without any calibration curve, but in reality when we want to measure we require parameters which need to be optimized or calibrated using known molecular weight. That is why these are relative techniques. And the molecular weight range for which these techniques are applicable are given here. And in all these techniques we need to be very careful about low molecular weight impurities, because as I described that these are colligative properties and the property of this nature depends on number of molecules. Hence, if there are low molecular weight impurities which will effectively increase the number of molecules in solution to a much larger extent, and there will be large error in these techniques. N group analysis is done using some chemical techniques, and this also gives number average molecular weight, and this is absolute measurement technique. Polymers with low molecular weight, especially if it is the value is less than 15,000. And the restriction is that we need to have techniques which can quantify the N groups very effectively. So, to apply this technique of molecular weight determination, we need to have polymers with distinct N groups which can be quantified by any chemical methods. And of course, care need to be taken about low molecular weight impurities. Similarly, ultracentrifugation techniques used to measure weight average molecular weight and Z average molecular weight. This is absolute technique and is only applicable for high molecular weight polymers. The disadvantage is that it takes too long time. Dilute solution viscometry is very easy technique, and it gives, as we discussed in few minutes back, it gives viscosity average molecular weight. It is a relative technique which is not very suitable for low molecular weight polymers. The advantage is that it is simple, fast, inexpensive technique, but disadvantage is that it is less precise and solvent dependent. Light scattering technique can be used to measure the weight average molecular weight and radius of gyration, and also polymer solvent interaction parameter, from which we can also get the chi value of chi parameter. This is absolute technique, and this is applicable to medium to higher range of molecular weight. Disadvantage is that it does not give good accuracy for lower molecular weight polymers. One of the best techniques for polymer molecular weight determination is gel permeation chromatography, or GPC. It gives number average molecular weight, weight average molecular weight, and also the entire distribution of molecular weights, which indirectly gives the dispersity. Gel permeation chromatography technique can be either relative or absolute, depending upon how we use. In most instances, in most laboratories, GPC techniques are used as a relative technique. That means molecular weight measurements are done using a calibration curve which is generated from known molecular weight of polymers. It is applicable for complete range of molecular weight of polymers, and disadvantage is while we use this as a relative technique, we need calibration, for which we need lot of polymer standard which are basically monodispersed polymer molecules with known molecular weight. We can also use this as an absolute technique, but for that we need this very expensive technique, and we require more sophisticated instrumentation for this. Now, for this course I will only discuss about the techniques which are of practical utility as of now. Nowadays, although these techniques are all available, but generally we do not use these techniques for measuring polymer molecular weight nowadays. Nowadays, the techniques which are used very frequently are N group analysis. So, I will discuss N group analysis. I will, as a representation from these four, I will briefly discuss the membrane osmometry, but these four techniques are not very used very frequently, but from as a representative I will discuss this membrane osmometry. And as this is very easy technique and can be used commonly in lab for a crude way of measuring molecular weight or quick way of measuring molecular weight, which may not require very accurate result. These are used nowadays for quick measurements of approximate molecular weight. So, I will discuss this dilute solution viscometry. I will also discuss light scattering and gel permeation chromatography. So, I will stop now. From next lecture onwards, I will discuss these 5 techniques which I marked now for determining polymer molecular weight.